Let's learn how to calculate the gravitational potential energy of objects like satellites that are not near the surface of the Earth. This will also lead into a discussion of escape velocity and black holes. First, please recall that the force that the Earth exerts on an orbiting satellite goes as the inverse square of the distance. In fact, our formula, F sub capital G, is equal to G, that's our gravitational constant, 6.67 times 10 to the negative 11 in SI units, times the mass of the Earth, times the mass of the satellite, over r squared, where r is the radius of the orbit. Now, let's consider the question, what is the work required to move the satellite from an orbit of r1 to an orbit r2? We can't simply substitute into the formula work equals force times distance, subbing in Fg for our force and r2 minus r1 for our distance, because, well, we've just seen F sub g is not constant from r1 to r2. It falls off as the inverse square. So we're going to think of the work done as the area under the graph. How do we find the area under the curve? This is why Sir Isaac Newton invented integral calculus, to find the area under curves. We're going to do a little integral calculus here to derive the formula for universal gravitational potential energy. You don't have to know the derivation, but you should know where it comes from, the area under this curve. That wiggly sign there is an integral sign. We're integrating from r1 to r2, our function gmm on r squared. The answer is, as shown here, negative gmm on r2 minus negative gmm on r1. Since our work done is a change in the quantity negative gmm on r, this is what we're calling the universal gravitational potential energy, E sub capital G. Now, it really bothers many people that there is a negative sign there in the formula for universal gravitational potential energy. Why should universal gravitational potential energy be negative? Well, let's turn around and ask the question, why should it be positive? Before, we had positive gravitational potential energies, but they were always given relative to some arbitrarily defined reference height h. They weren't really positive, they were just more positive, or rather less negative, than the reference height 0. This equation is still consistent with our mgh that we had before. The change in gravitational potential energy will still be positive when moving from a smaller radius to a larger radius. The smaller radius will have a smaller denominator and therefore be more negative. The larger radius will have a larger denominator and therefore be less negative. To visualize negative gravitational potential energy, we often picture gravity wells created by our masses. Far away from any mass, you're going to have zero gravitational potential energy. There's nothing to fall towards. As you approach the mass, well, you're falling down. You're losing gravitational potential energy. You're going down below that zero where you started. You're falling down a negative well. Now, if the gravitational potential energy plus the kinetic energy of the satellite is less than 0, you're trapped in that well. The satellite is gravitationally bound and will therefore orbit the Earth. The binding energy of any satellite is defined as the additional kinetic energy it would need to escape. Let's estimate the binding energy of the Moon. We're going to be given that the mass of the Earth is about 6 times 10 to the power of 24 kilograms. The mass of the Moon, much less, 7.35 times 10 to the power of 22 kilograms. The radius of the orbit, is being given as 3.84 times 10 to the power of 8 meters. The speed at which it's orbiting, if we do 2 pi r over a period of 28 days, is going to be 1.0 times 10 to the power of 3 meters per second. So the total energy of the moon, if we substitute into our equation 1/2 mv squared plus our negative gmm on r, is going to be a negative 4 times 10 to the power of 28 joules. We're just going to round here to one significant digit. This implies that the moon has a binding energy of 4 times 10 to the power of 28 joules. We would have to give that moon that much more energy to have it leave Earth's orbit completely, to escape. So if the kinetic energy is large enough that the total energy is 0 or positive, satellites escape the pull of Earth's gravity. To find the escape velocity, therefore, the minimum speed at which this occurs, and we're here assuming that the satellite is starting from the surface of the Earth in this equation. If it's not starting from the surface, put in a different radius. Set 1/2 mv squared plus our negative gmm on r equal to 0. Solve this for the speed. We wind up with the speed is equal to the square root of 2gm over r. M is the mass of the large object that we're trying to escape, here the Earth. Radius is the radius that we're starting from, here the surface of the Earth. Notice that the escape velocity is root 2 times the orbital velocity. Basically, it's 1.4 times the orbital velocity to escape. Now, let's think of some applications of this concept. A gas is made up of atoms and molecules with a wide range of speeds. In chemistry, you may have seen that these speeds are distributed according to what's called the Maxwell-Boltzmann distribution. There is some average speed in there, but some are moving much more slowly and some are moving much more quickly. The graph shown at the bottom shows the Maxwell-Boltzmann molecular speed distribution for the noble gases, helium, neon, argon, and xenon. Notice that for xenon, the speeds are much lower than for our lighter helium. This implies that since helium is moving so quickly, some of the helium is moving faster than the escape velocity of the planet. Some of it will leave. When these fastest particles escape into space, the remaining particles repopulate the distribution just at a slightly lower total level, and again, the fastest particles are lost. An atmosphere will bleed off its lightest gases over time. This is why our atmosphere is nitrogen and oxygen and the like, and not lighter hydrogen and helium. We have to continuously replenish our helium with basically alpha decay products. However, our massive gas giant planets with a higher escape velocity can have significant hydrogen and helium. Jupiter and Saturn are mostly hydrogen and helium. Lighter objects like the Moon or Mercury or even Mars cannot maintain much of an atmosphere at all. Now let's talk about objects much more massive than Jupiter or Saturn or even the Sun. A black hole is formed from the collapsed core of a massive star. For most of a star's life, the heat and the pressure created by fusion reactions in the core can support the star against its own gravity. Once it runs out of fuel for that fusion reaction, it starts to collapse. For light stars like our Sun, the collapsing material will eventually be supported by what's called electron degeneracy pressure. Basically, the atoms don't like being squished together any closer. If it becomes more massive, it'll even manage to squish those atoms together. In fact, it squishes the protons and the electrons together to form neutrons, and you wind up with a neutron star that is then supported by neutron degeneracy pressure. If even the neutron degeneracy pressure can't support a really, really large mass, something happens that is outside our understanding of physics. All that we know is that we have a mass, a very large mass, in a very small radius, something that is extremely dense. The surface of a black hole is defined as the position at which the escape velocity is equal to the speed of light. This is often called the event horizon. Anything that crosses this event horizon cannot escape, not even light. So let's find the radius of the event horizon of a black hole with a mass 30 times the mass of the Sun. Well, if our escape velocity is the velocity of light, we're going to use that in our equation for escape velocity. M is going to be the mass of the black hole, 30 times the mass of the Sun. And R is what we're going to look for the radius of the black hole, sometimes called the Schwarzschild radius. Event horizon, Schwarzschild radius, they're the same measurement. Putting in our numbers, we find that the radius of the black hole is only about 90 kilometers. We've got a mass 30 times the mass of the Sun in a space smaller than 90 kilometers. That's what we mean by incredibly dense.